Hello, can you hear me, please? Ayola Adebowaye Oyeka, can you hear me?
Yes, sir.
Sir, I think
Okay.
you are heard loud and clear. It's just if the student don't want to answer.
Okay, thank you, sir. I'm very grateful, sir. Thank you. I'm very grateful. 200 level, I welcome you all to cardiovascular physiology class. This is your first interaction with me in this precious class. I welcome you to LASUCOM. Today, I will be teaching you the first lecture in cardiovascular physiology. And when we discuss the cardiovascular system is one of the integrative systems in the body. And it functions similar to your endocrine system, your nervous system. These systems are involved in integrating several functions in the body. Now, having a foundational knowledge in cardiovascular physiology will help you in understanding cardiovascular diseases in the future. Because when you are opportuned to study the normal function of the body, the normal physiological processes that takes place in the body, it will give you the capacity to understand when there's a deviation in the physiological processes when you know the normal. If you now see the abnormal, you can compare and say, no, this is a deviation from the normal physiological processes in the body. Now, as the name implies, cardiovascular physiology. How is the cardiovascular physiology organized? When you see the cardiovascular physiology, one of the things you note is that there are two keywords that are there. You have your cardio and you have your vascular. When we say cardio, we are talking about the heart. And when we say vascular, we are talking about the vessels. When we mean vessels in the body, we talk of the veins, the arteries, capillaries, arterioles, venules. These are the veins, these are the vessels in the body, also your lymphatic system. Now, you also have a component that is more encompassing than the cardiovascular system. That is the circulatory system. In the circulatory system, we have not only the heart, the vessel, and the blood vessels, we also have the blood itself. And I know that Dr. Lumide is handling the blood session, body fluids and blood quite comfortably with every one of you. Now, when we mean the circulatory system, we mean the cardiovascular system, the blood, the lymphatics. And from where you are taught, from the little you are taught about lymphatics, you know that once the lymphatics, the arteries carries blood away from the heart. The veins carry blood to the heart. Now, the fluids that are left that the veins cannot carry to the heart is carried back to the cardiovascular system by the lymphatic nervous system. So that's the summary of the key organization of how these places look like. Now, generally, when we are discussing cardiovascular physiology, we can look at it in various ways, depending on what we are discussing and what is important to you. Somebody may decide that they want to look at the cardiovascular physiology in terms of the central circulation and the peripheral circulation. And when we mean the central circulation, we're talking about systems that cover the heart, brain, part of the sprinkling circulation. And when we mean peripheral, we are talking of the hands, the limbs, the lower limbs. And but for this lecture, we are looking at the pulmonary circulation and the systemic circulation. Now, basically, once a blood gets, for you to appreciate this, from the basics you have learned over the years in the cardiovascular system. When we say we have the pulmonary circulation, we have the systemic circulation. You know that the pulmonary circulation has to do with blood supplies to the lungs. And when we mean blood supply to the lung, the blood is carried from the right atrium to the right ventricle and then to the lungs. And in the lungs, the deoxygenated blood that is being carried is oxygenated in the lungs. And for the systemic circulation, the blood that moves from the lungs to the left atrium, to the left ventricle, and via the aorta to the systemic circulation, everything that happens in the system is what we refer to as the systemic circulation. So, what are the functions of the cardiovascular system? Remember, I've given you a gist that they play a role in integrating several functions, in bringing together several functions of the body. Now, some of the key functions of the cardiovascular system, one is that transportation of oxygen from the lungs to the tissues. That is to say, once the blood cells are oxygenated in the lungs, it is the responsibility of the circulatory system to ensure that blood is circulated. So if that oxygenated blood is circulated to all part of the body. Number two, once you also have metabolic processes taking place in the body, where your CO2 is generated, it is also the responsibility of the systemic circulation to carry those CO2 from those tissues to the lungs where they will be exhaled. Number three, is transmission of nutrients from the gastrointestinal system to all parts of the body. Here you also see where the CVS plays a role with the GIT. Once you have eaten a food, the food has been digested, it is the responsibility of the circulatory system to ensure that this particular nutrient is delivered to various parts of the body, and this will be done by the cardiovascular system. Apart from that, when you have transmission of waste products of cellular metabolism from tissues to the kidneys, so when you have metabolic processes taking place in your body, several substances are generated that are carried to the lungs, to the skin, and various other of the body by the circulatory system. Now, apart from that, you also have your circulatory system playing a vital role in conveying hormones from various endocrine glands to target tissues and organs. As you know, once you produce your hormone either from the thyroid gland located around the neck, you know that those hormones will not only act on the thyroid gland, or those endocrine hormone, those hormones react on various aspects, various parts of the body, and this will come into play if they are carried by circulatory system to various parts of the body. Apart from that, your blood cells that will be taking you on, the ones they are produced in any other part of the body, they are also carried to various parts of the body by your circulatory system. That is not the limit of the circulatory system. Infective agents, for example, if you have infective agents, maybe by mistake through your veins, you have microbes being being injected into your veins, or through any means, microbes gain entry into any part of your body. It is the circulatory system that will also play a role in ensuring that that microbe is thoroughly circulated through your body. Apart from that, they also, that's why, so you have cancer cells and the rest, your circulatory system also play all those roles. So those are the key things about key functions about the circulatory system. Are we on the same page? I hope so. I hope we are all on the same page.
Yes,
It
sir.
appears only a few of you are interested in this lecture. I know that your class,
Yes,
you
sir.
have over you
Yes,
have
sir.
over you have over 250.
We're on the same page.
Hello? Yeah, okay.
We're on the same page. We're on the same page.
We are hearing you,
Okay.
sir.
I have to be sure we're on the same page, because
We're on
at
the same-
times you'll be teaching students. You will be in Shagamu, and all your students will be in Kano, and you will think that you are traveling in the same bus, and whereas you are not in the same bus, you are on your own, they are on their own. By the way, now what we are going to also consider now is the heart. The heart. The heart lies in the left side of the chest, in the middle mediastinum. When you are doing your anatomy, you are going to be taught thorax, and they are going to teach you the anatomy of the mediastinum. So where the heart is located is called the mediastinum, and when we are talking of the coverage, the layers of the heart has what we call the endocardium, the inner layer of the heart, the endocardium, the inner layer of the heart. The heart has the myocardium, that is the muscles of the heart. And the heart is covered by what we call the pericardium. And the pericardium is the covering of the heart. Now, that is why they say the heart is enclosed in a double sac called the pericardium. Now, in between this double sac is where we have what we call the pericardial space, and that pericardial space is filled with small amount of fluid. But that is not the focus of our lecture. Now, the heart has a base, which is the broad superior portion of the heart. Now, if you look at the way the heart is structured in such a way that the part that is the base is the one that is above, is further above, and the part that is below is what you call the apex of the heart. So the base, it has a base which is broad, superior portion, and this base is the point of attachment of great vessels like your aorta, your pulmonary trunk, your vena cava. So if you look at this diagram, the part above that is broad is called the apex, and that's where you see all those, your aorta, your pulmonary, your vena cava entering through. And this pointed aspect that is below is what we call the base, the apex of the heart. The base is above, the apex is below. Now, somebody will ask a question: why should the apex of the heart be above, be below, and the base is above? The reason why this is like that is because was a very interesting question a student asked me several years ago. Because I never for once challenged. Well, that's the naming. Now, historically, what happened was that the heart was seen as an inverted cone. The heart was seen as an inverted cone. And once the heart is seen as so when the heart was seen as an inverted cone, you know that if you have a cone, the pointed edge is the apex, while the broad base is the base. So when you now have it inverted, it means the base will be above and the pointed end will be what? Below. And that's the reason why you have this, the heart has been named like that for several years. That's the way they taught my teachers, and that's the way the teachers of my teachers were taught. So the apex of the heart is lower inferior end, and the apex tilts to the left, tapering to a blunt point, which I've shown you earlier on. This is also a diagram showing what I've explained. So now the size of the heart. Now the heart is about the size of a clenched fist. So if you clench your fist, you have an idea of how your heart looks like, the size of your heart. And it's about 9 cm wide at the base, 13 cm from apex to the base, 6 cm from the anterior to the posterior border at its thickest point. And on the average, in adults, the heart is roughly between 250 grams, 200 grams, and on the average, it is 300 grams. And except you are diseased, somebody is diseased, have some heart pathology, the size of the heart is generally constant in an healthy individual throughout life. So what are the chambers of the heart? These you have also known, for several years. There are 4 chambers of the heart: right and left atria. You also have right and left ventricles. The atria received blood returning to the heart, and the atria received this blood via especially the atria generally, but the right atria received blood via superior and inferior vena cava. The ventricles generally point out blood from the heart. And for physiological purposes, this I want you to put in your heart. Generally, the amount of blood pumped out from the heart from the right ventricle per minute, we call it cardiac output. The amount of blood pumped out of each ventricle per minute is called cardiac output. Cardiac output from the right is equal to cardiac output from the left. Cardiac output from the right is equal to what? Cardiac output from the left. You must know this and you must never forget it. So the atria so now if you look at, so let us now comment briefly on the individual structures, the atria, the ventricle. The atria have thin, flaccid walls. The atria have thin, flaccid walls corresponding to their light work. The atria have thin, flaccid work corresponding to their light work. Let me see, as we go on in physiology, you are going to understand why they say the work of the atria is the light work. Now, if you look at the blood that moves into the heart from the general circulation into the atria, into the ventricle, 70% of the blood that moves into the ventricle moves into the ventricle passively. 70% of blood that moves into the ventricle moves into the ventricle passively, while only 30% is what? Pumped. The remaining 70% moves into the heart passively. Only 30% of atrial contraction. Only the atria only pumps 30% of the blood. So the work it is doing is light. Meaning that if 70% of the blood moves into the right ventricle via passive activity, then you ask yourself, why do we really need the atria? So the work is light. So the walls need to be thick. And as you know, is that you have your structure function relationship. You know how heavy the work the heart does. We tell you how thick it will be. So, but the ventricles, as we know, does more work. The ventricle have thicker walls throughout, though that of the right ventricle, the right ventricle pumps into the ventricle have thicker walls, though that of the right ventricles that pumps into low pressure bed, pulmonary circle is 2 to 4 millimeter thick, and it is not as thick as the left ventricle that is 8 to 10 millimeter thick. Now, don't forget, we said that right the right part of the circulation, the pumps blood to the pulmonary circuits. The pulmonary circuit is pulmonary, lungs, where the blood is oxygenated. You now have the systemic circulation, where the left ventricle pumps blood into. As you know, the systemic circulation is bigger than the pulmonary circulation, which is limited. So as a result, the right ventricle is thinner because it pumps blood just to the pulmonary circulation, but the left ventricle is thicker because it pumps blood to the systemic circulation. I hope we are still on the same page. You know, I hope we are on the same page, or I'm on my own. So
Yes, sir.
Yes, sir.
that is the reason why you have 3 to 4 millimeters of thickness, and for the right ventricle, and 8 to 10 millimeter of thickness to the left ventricle. So now the atria are separated by interatrial septum, while the ventricles are separated by the interventricular septum. The atria are separated from the ventricles by your secondary school. All these are secondary school stuff. By your atrioventricular valves. The right atrium is separated from the right ventricle by means of the tricuspid valve, while the bicuspid or mitral valve separate the left atrium from the left ventricle. So the cusp of the valves are connected to the conical muscles on the floor of the ventricles by string-like tissues called chordae tendineae, and the opening of the right ventricle into the pulmonary trunk is guarded by pulmonary valve. So now when the right atrium wants to pump blood into the pulmonary trunk, it is guided by a valve called the pulmonary valve, while the aortic valve is at the opening of the left ventricle into the aorta. So you have for each side you have two valves, the atrioventricular valve and the semilunar valves that has been described shortly. So these are the structures again. So these two valves, that is the semilunar valves, the pulmonary valve and the aortic valve, they are both called semilunar valves. So they are both called semilunar valves because of their shape. Now, what are the value of valves? The valves ensure unidirectional flow of blood through the heart. The valves ensure unidirectional flow of blood through the heart. So let us comment briefly on the right side of the heart and also the left side of the heart. These are the things, basic secondary school stuff. So the right heart serves the pulmonary circuit, as we have discussed, and we know that the designated blood from all over the body returns to the right part of the heart or the right atrium via the superior vena cava and the inferior vena cava. All the blood coming from above the heart is drained towards the heart by the superior vena cava, whereas all the blood coming from below the heart is drained towards the heart by the inferior vena cava. The deoxygenated blood is pumped into the right ventricle, where it is pumped into the pulmonary trunk, from there to the lungs, where it is oxygenated. So the pulmonary trunk on its own is a large artery as you know from secondary school, we are told that all arteries carry oxygenated blood, except what? All arteries carries oxygenated blood, except what? Somebody should complete this for me now.
Except
The
the
pulmonary artery.
Beautiful. Except pulmonary artery. All arteries carries oxygenated blood except pulmonary artery. And all veins carries the oxygenated blood except what?
Pulmonary
pulmonary
vein.
vein.
Beautiful. Now, remember that we just said that the blood that is pumped from the right ventricle is pumped into the pulmonary trunk. And the pulmonary trunk is a large artery that divides into left and right pulmonary arteries that transports blood to the pulmonary beds. And the alveoli, where oxygen is picked up, that the alveoli where the oxygen is picked up after the carbon dioxide in the deoxygenated blood has been unloaded. So you remove the carbon dioxide, you upload the oxygen. The oxygenated blood flows back to the left side of the heart through the pulmonary veins on each side. So this is how the blood flows. The blood flows from your right atrium, right ventricle, pulmonary trunk, pulmonary arteries, pulmonary capillaries, pulmonary vein. You have your pulmonary circulation. Right artery, right ventricle, pulmonary trunk, pulmonary arteries, capillaries, and then, by the way, the left side of the heart, oxygenated blood flows into the left side of the heart through the left atrium, and the left side of the heart serves the systemic circulation. So blood flow from the left atrium is pumped into the left ventricle, from where it is pumped out through the aorta to the other arteries, supplying oxygenated blood to the heart. All these are basic physiology. So after circulating through the body, the blood once again becomes deoxygenated and returns to the heart, the right side of the heart, through the superior and inferior vena cavae. So therefore, you have your left artery, left vein, aorta, arterial networks, capillaries, vein, systemic circulation. And the key difference between your between the pulmonary circulation and the systemic circulation is that pulmonary circulation is a low pressure bed circulation, is a low pressure circulation, whereas your systemic circulation is what? High pressure bed circulation. I hope that is clear. Now we'll comment briefly about your skeletal muscle. So normally this cardiac muscle that you are being taught, you are still going to be taught nerve and muscles extensively. So the cardiac muscle is such that I will do everything I'm teaching you is just tip of the iceberg, so you still learn more about cardiac muscle than nerve and muscle. But because I'm 100% sure you have not been taught nerve and muscle, so we'll just talk briefly about them here. So cardiac muscle is striated in nature. Cardiac muscle is striated in nature, and the cardiac myocytes are short, thick, branched cells, and they measure about 50 to 100 micrometer long and about 10 to 20 micrometer wide. The cells have one centrally located nucleus. They contain numerous mitochondria. I want to ask you a question. If they tell you that a cell contains a lot of mitochondria, what does that tell you about the cell?
It uses a lot of energy.
Beautiful. It tells you that such a cell uses a lot of energy. and those energies will be generated through metabolic processes that will be carried out by your mitochondria. So if they say, this you tell, and a lot of mitochondria, it tells you that something is in that tissue. And that is the reason why we say many of the structures in the body, you have quite clearly that um, um, quite clearly that it is the quite you have quite clearly that this demonstrates what we call structure function relationship. Structure function relationship. You have the structure and you have the function is carrying out. The structure is in terms that it contains a lot of mitochondria that is ready to carry out several processes. So the sarcoplasmic reticulum is not so well developed and it lacks terminal cisternae, and as a result, calcium ion are taken up into the T tubules from extracellular fluid directly. You can see this is the structure of the how your cardiac muscle, how they look like. You have those lines called intercalated disc. You have cross striations. You have your myocytes. You have the nucleus. And this is how, if you look under the microscope, if you have a typical histology of the cardiac muscle, this is how it looks like. And it has intercalated disc, those lines that appear blue, this purple or blue, in the structure is there. So let us comment briefly on the intercalated disc of the heart. So the myocytes are joined by thick connections. So the myocyte, when we mean the myocyte, we mean cardiac cells, the cardiac muscle cells. So the cardiac myocytes are joined by thick connections called intercalated discs, which appears as dark lines under the microscope. Each intercalated disc has three distinctive features. Each intercalated disc has three distinctive features. Number one, we have what we call interdigitating fold. The plasma membrane, when we mean the plasma membrane, we are also discussing about the cell membrane, basically. It's the same thing. The plasma membrane at the end of the cell is folded, and the folds of adjoining cell interlock with each other, thereby increasing the surface area of the intercellular contact. So you can see some of those locks, how the so now these are some of the diagrams. Some of them are not so clear, but I think you can still manage to see them. You can see the connections between the cells. Connections between the cells. Number two is they also have what we call mechanical junctions. So we are itemizing the features of the intercalated disc. We have said one, they have interdigitation folds. Two, they have the mechanical junctions. There are two types of mechanical junctions joining the cells together. We have facial adherence. This is the most extensive, and it is interrupted by your desmosomes. We also have another mechanical junction called desmosome. These hold two cells together and enable the tissues to resist mechanical stress. The cells are separated by the cells are separated by a small group, by a small gap which is spanned by a line of mesh of glycoprotein filaments. Now, all these mechanical junctions help the cells to resist mechanical. You can see the desmosomes. You can see these desmosomes in the cells. They play a role in helping the cell to resist stress. So now the key junction of this key function of these mechanical junctions is to prevent myocytes from pulling apart when the heart contracts. And if you see all the way the structure of the heart is, you have interdigitating folds that lock the cell. You have the mechanical junctions that help the cell to withstand stress. All this tells you that the cell does not want to pull apart because the massive contraction taking place in the heart the contraction to keep the heart continuously. Unlike other muscles, the heart continuously contracts. Your heart cannot stop contracting the way you are. You just die and collapse immediately. The heart continuously contracts. So there must be something there to hold it together, to give it life, to prevent it from tearing apart. And that is why you have this multiple layers of structures to keep the heart strong, to keep the heart into place, to prevent processes that will tear the heart apart. Thirdly, you also have in this intercalated disc what we call the electrical junctions. These form channels that allow ions to flow from cytoplasm of one cell directly into the cytoplasm of the next cell. The joints enable each myocyte to electrically stimulate its neighbor so that the entire myocardium of the atria and of the myocardium each acts as though it were a singular cell, and it is responsible for the syncytial property of the heart. Now, the beauty of this nature of this cell, from the ECF, once you take up electrolyte, it can freely flow into the next cell, without any problem, directly to the next cells through one cell. The beauty of this is that that when we are discussing about action potential, electrical connections, among certain, it is this electrolyte that determines how these cells will be stimulated. And once you have this freedom of movement of electrolytes from one cell directly into the next cell, it enables the heart to act as one, to contract as one, and to act as though the heart is just a single cell. And that is why if you start seeing heart acting as one, contracting at the same time as if they are one cell, the heart itself will be acting as a syncytium. It is called a syncytium. In this particular case, the heart is considered as a functional syncytium. In terms of its activity, in terms of working together, the heart works as though it is a single cell because of the capacity of this electrolyte that causes the changes in membrane potential to be able to flow directly from one tissue to the other. So again, is that is not about intercalated disc. But let me also add this particular one to it about the nature of the cardiac myocyte. Now, if you look at cells in the body, the cells in the body are of different types. We have the cell we call labile cells. Like those cells, once they are damaged, they can easily regenerate back to the original state. Let me give you an example. If you look at your tongue, for example, many times you put what is off on your tongue. If you use what is off and you burn that part of your tongue, like for a day or two, you may not feel any taste in that particular aspect of your tongue because that place is dead. And after a few days, you see complete regeneration of those tissue, and the tissue will be normal as if nothing happened on that spot. Those cells are labile cells. There's some cells in the body that if they are damaged, the cells cannot recover its structure like before. The cardiac myocytes are that type of cell. They are incapable of mitosis. They are incapable of cell division. So when they are damaged, what will happen is that the repair of the cardiac muscle is by fibrosis. The repair is not by normal tissue replacement, no. What we have is the scar, fibrous tissues. You don't forget in your hands, when you get injured. At times it might heal without any scar, especially in the young. But at times it will heal and you see scar on that part that this is the scar of where I got injured. In the cardiac muscle, that is the way it heals. Now, for example, how can the heart muscle be injured? That muscle may be injured. Maybe you have your myocardial infarction. You have blood supply to one part of the heart being cut off temporarily, and the part of the heart got damaged. Once that part is damaged, even if you start to restore blood, what will happen eventually will be that part will heal by fibrosis. It will not heal by. So somebody that is doing echo, and once it is by fibrosis, it will not move like other part of the heart. So someone that is doing echocardiography may sense that there is motion changes in this part of the heart, because the heart is not, that part has not healed by normal healing, it has healed by fibrosis. As a result, because it has healed by fibrosis, um, 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 if it has healed by fibrosis, the part of the heart will not that part of the heart will not heal, will not function as if it is normal tissue. So the blood supply to the heart is a part we will discuss briefly now. We also come back to it later. So the heart is supplied by right and left coronary artery, and they are the first branches of the heart arising just above the aortic valve. Coronary venous blood is collected by the veins, the largest of which is the coronary sinus, which runs in the posterior AV groove and opens into the right atrium. So the nerve supply to the heart, the parasympathetic nerve supply to the heart is via a vagus nerve that mainly supply the atria, SA node, AV node, and the conducting tissues. These conducting tissues of the heart is the part we are going to visit later. The sympathetic supply is from upper thoracic and inferior cervical ganglia, and they also supply parts of the heart. Now, so therefore parasympathetic mainly affect heart rate and conduction, which we are going to emphasize later, and sympathetic affect force of contraction in the heart, into the heart rate, contraction in addition to heart rate and your conduction. Also, the heart also has sensory fibers that originate from the heart. And with these sensory fibers, the heart can feel pains. Because if there's no sensory fibers in the heart, even if the heart is having problem, you will not feel the pain. And in patients with diabetics, they lose this sensory action of the heart, and that's why they have what we call silent myocardial infarction. So this sensitive part of the heart ensures that the heart also have cardiac pain when stimulated. So these are the basic so this other aspect of the lecture, this briefly with the components of the vasculature, that is the vascular system. In this lecture, I'm not focusing on uh, we'll discuss it on the histology of the arteries and the veins, which would be discussed later. Now, the arteries. So, since we have been focusing more on the arts, but this other part of the lecture will focus more on the arteries. So, the arteries are thick walled with extensive elastic tissue and smooth muscle. The arteries are under high pressure from the heart. The blood volume within the arteries is referred to as the stress volume, and this delivers original blood to the tissues. The arterioles, from the arteries, blood gets to the arterioles, and these are the smallest branches of the arteries. The arterioles are the site of highest resistance in the cardiovascular system. They are called resistance vessels. They have a high smooth muscle wall that is extensively innervated by the autonomic nervous nerve fiber. It tells you that stimulation of the parasympathetic or the sympathetic nervous system can have a role to play in determining the size of this structure. We have arterial resistance that's secreted by the ANS, these have been mentioned. You have our arterioles, you have your alpha 1 adrenergic receptors on the arterioles of the skin and splanchnic circulation. When we are talking of splanchnic circulation, we are talking of the intestinal circulation, the circulation around the GIT. Now we also have what we call the beta 2 adrenergic receptors on the arterioles of the skeletal muscles. I believe that I know we say tissue about adrenergic receptors in his lecture, in his ANS lecture. I think Doctor, I know he's teaching you ANS, or Dr. Salami, one of them will be teaching you, extensively on this. So you have our capillaries. Capillaries, they lead on from the arterioles. They have the largest cross-sectional area and total cross-sectional area and total area and total. They have the largest total cross-sectional area apart from that, they also consist of a single layer. The capillaries are regarded as the exchange vessels in the body. They are the areas where you have exchange of nutrients between the tissues and and blood vessels. Now they have thin walled because they are exchange vessels. They can't be thick. If they are too thick, exchange will not take place between them and the tissues. And they have a single layer of endothelial cells surrounded by basal lamina. They are thin walled at the center of exchange of nutrients, water, and gases. Capillaries merge to form venules. Capillaries merge to form venules. Venules merge to form veins, and your small vein progressively merge to form larger capillary veins, and the vena cava return blood to the heart. So we have our veins. The veins are thin walled. They are under low pressure, contain the highest proportion of blood in the cardiovascular system. Hence, they are called the capacitance vessels. Apart from what you learned in secondary school, your capacitor store charges. The same way your veins, they are the highest, they have a lot of blood is contained in them. And all this you must know. Blood volume contained in the vein is referred to as stress blood volume. The way the blood in the arteries are referred to as stress volume because they are under high pressure, but the blood in the veins are under low pressure and they are referred to as the unstressed volume. The veins are innervated by autonomic fibers. Most veins, especially those of the lower extremities, have valves, and the function of these valves is to ensure a unidirectional flow of blood toward the heart. The purpose of the valve to ensure the unidirectional flow of the valve. And you will know that in this sentence that most of the valves are vein, not all of the valves. So normally the routes of blood flow is as follows: the heart, arteries, arterioles, capillaries, venules, veins, and these are the direction in which blood flow. The blood flow from the heart, but when the left ventricle pumps blood into the circulation via the aorta, from there it flows to the arteries, from there to the arterioles, where with the high resistance vessel in the body, from the arterioles to the capillaries, where we have exchange of nutrients, oxygen, gases between the capillaries that has once that has one cell that have one layer of cell, and you have the capillaries merging to form the venules and the venules merging to form veins, and the veins ultimately returns the blood back to the heart via the superior and inferior vena cava. So, however, there are two exceptions to this. You have the portal system. This you are going to learn more in anatomy. So, the portal system, in this you have between the hypothalamus and the pituitary gland. You also found this in the kidneys, between the intestine and the capillaries. In the portal system, blood flow from capillary to capillary. This you will learn more later in your physiology. Also, you have your anastomosis. Two veins or arteries merge with each other. You can have arteriovenous anastomosis. The capillaries is not in this one. Blood flows from an artery directly into a vein through the capillary. You see this in the toes, finger, palm. And in arterial anastomosis, two arteries merge and provide collateral alternative routes of blood flow. You have this in the coronary circulation. When we are discussing coronary circulation, we also have this taking place. So you have the venous anastomosis, very common. They provide several alternative routes of drainage from an organ, so that blockage of one vein is rarely a life-threatening situation. So we can always have other veins taking place, taking the blood away from the area where vein has been blocked. So and that reason why, if they are taking blood from you, most of the time, a good number of time, sometimes when you take blood from a vein in the hand, you damage the vein. And once you damage the vein, other veins will still drain that part of the body, and after a while, the vein may recover. So we have some few hemodynamics in physiology, and as I always tell students, these hemodynamics principle are principles derived from physics, and you must also go back to physics to review some things. So the velocity of blood flow in the vessels The velocity of blood flow in the vessel can be expressed as velocity and your it appears I'm not too fast. Hope you're on the same page. Are we on the same page?
Yes, sir.
Yes,
Yes, sir.
yes, sir.
Uh-uh.
Yes, sir. We're on the same page.
So I want to be sure
Yes,
because
sir.
it appears I'm running too fast. You know, students are funny. As I said earlier, you might be in Idimu and your students will be in Molete in Ibadan. So I always like to ask the question to be sure that we are on the same page. That's not that you're on your own. Students will just leave you. They say you're on your own. Whereas it's when and you will not know that you're on your own until when you start asking them questions in the exam and you start marking their script and they are getting 0, 0, 0, 0, 0. And the next thing is that they did not. Okay, what? You can ask. Somebody wants to ask a question. You can ask your question, please. You can ask your question. Okay, beautiful. The mediastinum is where the heart is located. The mediastinum is where the heart is located. The mediastinum is a space where the heart is located. But the heart, it is not it is the location of the heart. This is mediastinum, you know. But the heart itself has covering that what covers it. The mediastinum is the location of the heart, whereas what covers the heart is the pericardium that covers the heart. Mediastinum is where the heart, the space where the heart is located. So the velocity of blood flow, can be expressed by the equation V over blood flow over the cross-sectional area, and velocity, and this tells you that velocity is directly proportional to blood flow and inversely to the cross-sectional area at any level of the heart. Velocity of blood flow is higher in the aorta with a small cross-sectional area than in the sum of all capillaries that have a large cross-sectional area. Now, blood flow is also expressed as change in pressure gradient over resistance, and from this, blood flow is driven by pressure gradient. So the difference in the pressure gradient between two structures will determine the direction in which the blood pressure, the blood will flow. So if you have a place of lower pressure, blood will flow in that direction, and blood flow from a higher pressure to an area of lower pressure, and blood flow is inversely proportional to the resistance of the blood vessel. Blood flow is inversely proportional to the resistance of blood vessel. So let us comment briefly on resistance. Resistance of blood flow is affected by the following factors. You have your resistance equals to H of eta length multiplied by length of vessel over your pi raised to power 4. Meaning that this implies that from this equation, resistance of blood flow is proportional to the length of the vessel and viscosity. When viscosity of blood is increased by an increasing hematocrit. When we mean increasing hematocrit, let me quickly explain to you because I don't think you have done that bit of blood. When you are talking of hematocrit, if you centrifuge, we're talking of briefly, we can say PCV. PCV, we can say PCV briefly, you can temporarily use it as your PCV. But once you centrifuge blood and that aspect of blood that is, I've not just said, I've not centrifuge blood. Why will I explain something to you? Okay, let us assume. So if you have blood, if you pick the blood, for example, the blood has the solute part and the liquid part. That solute part, how the content of that solute part is what we refer to as the hematocrit of the blood. So the higher the solute part, the more viscous the blood is. It's similar to you having a fluid. For example, you have a water. For example, if you are putting, for example, you have water now, ordinary water. The water is not viscous. But if you are putting oil, for example, in the water, or you are putting garri in the water, it becomes more viscous. Because you're adding more solute to it. When the viscosity of blood is increased, for example, by an increasing hematocrit, the resistance will increase, and this will decrease blood flow. So whenever you have an increase in viscosity, it will decrease blood flow. This, as I remember when I started, I said these principles that are being used here are basically physical principles used in hemodynamics in physics. And because that is what that is why if you are looking at all these sciences, they are interrelated. However, the effect of change in viscosity in vivo, what we mean in vivo, within the organism, not in vitro outside, differs from the prediction of this theory. In large vessel, increase in hematocrits. In large vessels, increase in hematocrits leads to increase in viscosity. In smaller vessels with less than 100 micrometer, viscosity change in hematocrit is much less. But in large tissues, once we increase the hematocrit, it increases the viscosity. So this is because difference in the nature of blood flow through small vessels, so that the next change in viscosity is considerably smaller in the body per unit change in hematocrit. So little changes in hematocrit therefore have relatively little effect on resistance inside the body, unlike what happens outside. When you are describing it outside, it can be different. So radius and resistance. The relationship between radius of a vessel and resistance is very powerful. If the radius of a blood vessel should decrease by 2, the resistance will increase by a factor of 16, as displayed in the formula that I showed you earlier. So that it's in the formula that I showed you earlier. You can check it up later. So there's another concept with regards to flow, which we are also going to discuss later: laminar flow and turbulent flow. Laminar flow is a streamline flow where turbulent flow is not. And what is used to predict this flow is what we call the Reynolds number. So Reynolds number is change in velocity change. You can ask your question, please. You can ask your question, please. Okay. Remember, I said that the size of an adult heart varies between 250 to 300, with an average of 200 grams. And I said that the average size of that heart is constant throughout life. In that is sort of an adult heart. It is constant throughout life. We have a range. The range I gave of 250 to 3 to is so those range is across life. But it is constant in individual except you have a disease. Teniola, please ask your question, please. Teniola, can you ask your question, please? Teniola? Okay, maybe she has changed her mind. So laminar flow and turbulent flow, Reynolds number, predicts this. So when Reynolds number is increased, there is a greater tendency for turbulence. And the Reynolds number is increased by decreased blood viscosity. Don't forget that we have said, ask your question, Kennedy, please. Can you ask your okay. Now you raised the question that what do I mean by laminar flow is streamlined? What I mean by streamlined is organized. It is in layers. Laminar flow is in layers. Laminar flow, you have your flow in layers. It is organized. Unlike your turbulent flow, as the name implies. And okay, what is laminar flow related to? I've explained that the streamline is in layers. That is how it is described. Now, in explaining the laminar turbulent flow, one of the reasons why we also bring up that topic is when you are, yes, That's the average. That is the average of the so now the uh, okay. Yeah. You are okay. Okay. You're asking several. Wait, somebody ask you're let me ask. I've seen like two or three questions at the same time. Let me now. Somebody asked the question, what is laminar flow related to? Now, when we are discussing blood pressure, the importance of laminar and turbulent flow will be discussed, because that concept of laminar flow and turbulent flow is the concept that we used in the measurement of blood pressure. You know, as the way you are, the flow in your body is moving, no problem. But when we tie cuff around your hand, for example, and we inflate the cuff, by the time we release the cuff, what the flow will just rush down. You know, that's an example of your turbulent flow, which we are going to discuss during measurement of blood pressure. We are going to discuss that in more detail. Somebody asked the question that um, I said that the deoxygenated blood will deoxygenate in the lungs. How does that process take place? Now, in the lungs, you have layers they call it the respiratory membrane. You know, once the blood gets to the lungs, you have the respiratory membrane. Don't forget, we have said that we have capillaries in the lungs, in the respiratory membrane. It is through the capillaries that the oxygen is delivered, the oxygen is delivered to the blood, and the CO2 is moved on to the lungs, and some of this CO2 are exhaled. You know, they are exhaled where you have your oxygen being uploaded
During
into the blood
expiration.
so it has the level of the respiratory membrane that this process takes place. Dr. Abidoye will teach you about respiratory membrane, you know, where you understand layer by layer how this process takes place. But it is at the respiratory membrane that this process takes place. So when Reynolds number is increased, there's a increased tendency for turbulence, and it is increased by decreased blood viscosity, such as in such as in anemia, and also increased blood ratio as in narrowing of blood vessels. You know, the turbulent flow is one of the bases on which measurement of blood pressure using the sphygmomanometer rest, which we are going to discuss later in our physiology. So capacitance, compliance, this is the distensibility of the blood vessels. The more elastic tissue in the blood vessel, the higher the elastance, the lower the compliance. Capacitance is inversely proportional to elastance, and the vein is the largest capacitance vessel in the body. Capacitance is directly proportional to volume and inversely proportional to pressure, as veins are capacitance vessels because capacitance is more greater in veins. This means that the more blood is contained in the veins than in the arteries that have less compliance and more elastance. A fall in venous capacitance leads to shifting of blood from veins to the arteries. And one of the things that causes fall in capacitance is your sympathetic stimulation that causes vasoconstriction, and you have blood moving from the arteries. Arterial capacitance decreases with age. Arterial capacitance decreases with age since the arteries become stiffer and less distensible as a person grow older. So pressure profile in the blood vessels, as blood flow through the systemic circulation, pressure decreases progressively because of the resistance to blood flow. Resistance decreases, pressure decreases. Therefore, pressure is highest in the aorta and lowest in the vena cava. The largest pressure in the arteries or core are called the arterioles because they are the site of highest resistance. Mean pressure in the aorta about 100 meters of mercury. At the end of the arterioles, 30 meters of mercury. At the end of the capillaries, 12. At the vena cava, 4 meters of mercury. So this is the last slide for our lecture today. Um, If you have questions, you can ask before I will call it a day. If you have questions, you can ask. If you have questions, you can ask. I'm surprised that many of us is not attend the lecture. Any problem? Or are they joining via the YouTube? Please, are the pharmacology students with us?
Yes.
Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
I know that you are about 150. Where is everybody?
Yeah, what
Some
are
are
you?
on YouTube.
Yeah, some are on YouTube.
Some join the
Okay.
YouTube channel.
Okay, I want to be sure that we are on the same page.
My speaker they on. My me on mute.
I heard your voices now. My speaker they on. I know some of you will not join the lecture. Maybe some of you will just be pretending you are in the lecture. Maybe you are on YouTube watching Tribe of Judah or Netflix watching Tribe of Judah instead of you to come and listen to lecture.
Sir.
So if you have your question, ask before we close the lecture.
Sir.
Ask your question, please, so I can provide
Someone
answers
asked
if I
a
can.
question that how is the oxygenated blood converted to oxygenated blood? From my understanding, I believe that during respiration, when we inhale oxygen, we breathe in oxygen. So the deoxygenated blood coming from the inferior and superior vena cava, which enters the right atrium then it is through the pulmonary, then it picks up, it releases carbon dioxide in the lungs and it picks up oxygen. So that's where the deoxygenated blood is converted to oxygenated blood, which now enters the left atrium through the pulmonary veins.
Hello. I offered an explanation. You are offering your own explanation. You are still learning, though, and you have to listen. What you have explained is juju, is voodoo physiology. I have explained real physiology to you. You are bringing your own explanation. Let me tell you, at their explanation that is appropriate for every level. The explanation for your own level is what you are saying. Physiology, that explanation is too basic for you. You understand? When she asked the question, I thought she was saying what is more advanced. That is why I gave what is more advanced and what we expect you to start saying after that 200 level. Once the blood gets to the lungs, we have what we call respiratory membrane. You have your alveoli, you have your capillaries. At that level, what you have the blood carries the blood cell, the hemoglobin of the blood helps in carrying your oxygen, your CO2, it plays the role. Once the deoxygenated blood, actually, I'm talking of your hemoglobin, once they get to the lungs, it will unload the CO2 and upload the oxygen. That is how oxygenation takes place. That is at the level of the respiratory membrane that exchange takes place. Once it uploads the CO2 and once it's offloads the CO2, it is through respiration, it is expired. And once it uploads the CO2, the oxygen, the oxygen now, the oxygenated blood now moves into the left atrium and to left ventricle and is pumped throughout the body. So it's a level of respiratory membrane in the lungs that exchange takes place. You know, if you want to understand physiology at physiology level, what every day we share more light on for you when you are doing your respiratory physiology. If you have more questions, you can ask. If you have more questions, you can ask.
So I think some people had some questions in the chat box. So I think some questions in the chat box.
Let me see whether. Okay, please, sir. You said that we should learn a formula. I can't. Okay, you said we should learn a formula. Okay, I showed you President formula. Is all the formula in this slide. They are the formula. All of them you should learn. Sir, you said we should learn calculation under this formula. Yes, you should do. Sir, does higher and low pressure work? Sir, how does higher and low? No, that is not what we mean. Somebody asks, how does higher and low pressure? No, that's not what we mean. What we are saying is that we have low pressure bed. For example, you will see the last study I showed you. I showed you the average pressure you see in various beds, various parts of the vascular system. Now, for example, if you are pumping water from here to Ibadan, you can't get the same pressure at every point of that pressure bed. You can't. Some you will see the same you will see at the early part, you see very high pressure, and as the pressure goes down. That is one. Again, I mentioned with regards, so in the vein, we have very high, the vein is a low pressure bed, is unstressed. The arteries are high pressure bed. That's the number one. Number two, I said pulmonary circulation is a low pressure bed, and you have a systemic circulation is a high pressure bed. I hope I'm clear. So how does the high pressure so what determines? I think I've explained that too. I think I've explained your question, except you have anything I've not explained. Okay. 2 new messages. What are the new messages? Okay. So I think I've answered your questions. I've answered your question, and you wouldn't have not answered if you have not answered. But I think I have answered all your questions. I think I have. So ideally, I should teach you in the afternoon, but I won't teach you in the afternoon today. Next week, our lecture will be in the morning and afternoon. So go and read. I will send some assignments to you via your class rep. I expect your class rep to group all of you into group of 10. You'll be submitting your assignments in that group of 10. Each assignment I give to you, submit it in groups of 10. I wish you the best. Have a nice day.
Thank you, sir.
Thank you.
So let all of us thank the ICT department of. Let all of us thank the ICT department of LASUCOM for helping us out with our lectures today. So ICT department, we are very grateful for setting up this lecture.
Department.
So you must always appreciate them for the good work, for putting up this for.
No.
Okay, have a nice day.
Thank you, sir.
Enjoy yourself.
Have a nice day.
Yeah.
Yes, sir.
Hello, sir.
Hello.
Hello, sir. So I this slide for sir.
No, I won't give you. You go and ask your seniors. They have the slide. They'll give it to you.
Okay, sir. Thank you, sir.